Hello, this is Sherry Kraber. Thank you for attending today's webinar. We are going to be talking about the keys to analyzing a response surface design. This is kind of a follow-up to a webinar that I did 3 weeks ago on the keys to building a response surface design. So if you want to know more information about that, you can go to our website and check out the recorded on-demand webinar for the part 1 of this. Today we are going to be focusing entirely on analyzing a response surface design, and we'll be using a central composite design as an example. To prevent audio disruptions, we're going to keep everybody muted today. You can post questions in the question area. If I don't have time to address them during the webinar, I will definitely send you a reply via email afterwards. You can send long-term questions to stathelp@staties.com. And if you can, provide your company name and your serial number if you have it, that would be welcomed. The slides and a recording of this webinar will be posted on the webinars page of the Staties website within a day or so. I will be using Design Expert version 13 today, and we just released this on January 4th. I would like to invite you to attend next week's webinar on Wednesday, February 17th. And that will, Martin Besner will be going over kind of what's new in Design Expert version 13. So that would be a great introduction to the new version. I may comment on a few things as I go through the analysis today. If you want more information on analyzing factorial and response surface designs, I would invite you to attend our live distance learning modern DOE for process optimization workshop. The next one will be held in the middle of April. This is the agenda I'm going to follow today, and this follows the path that we take through Design Expert software, starting with the fit summary, and then going into the ANOVA and the general statistics about a model. We'll be talking about diagnostics just fairly briefly, and I will touch on options for model reduction, and then kind of wrap up with final confirmation runs. And basically, I'm just going to be showing you how to do all of this in Design Expert. The case study that we're using is one that you can find in Design Expert, any version that you have. Go to the help system, go to tutorials, and you'll find the one called response surface chemical conversion. And that central composite design features 2 responses, percent conversion and activity. I will probably only be looking at the first response today. There are 3 process factors: time, temperature, and catalyst. And the experimenters split their design into 2 blocks so they can run it over 2 days. So the first block will have our factorial points plus some center points, and then the second block will have the axial points. Just a reminder of this design and how it's laid out. A central composite design looks basically like this. It has the factorial cube portion, and we're running that in the first block. That allows us to estimate our linear effects and 2-factor interactions. We also have center points that combined with the axial points help us estimate our quadratic effects. The center points are replicated to estimate pure error. And you can see we broke the center points. Let me go back a slide. We're breaking the center points into the 2 blocks, so they form a common base to tie the blocks together. And finally, we have the axial points or the star points that, again, help pull together the information for the pure quadratic effects. These axial points are located on the outsides of the box. Pull you out a little bit, and they are statistically positioned to give you the best prediction information within the box, within the cube, which is still your area of interest. All right, so here's an outline of the analysis procedure that we use. We're going to start with basically deciding if we need a response transformation. And to be honest, we start with no transformation. Now, if you're using any older version of Design Expert, this first button actually says transform. Version 13, we have added additional modeling techniques like Poisson regression, and in version 12 we added logistic regression. So because we are in the process of building up those additional modeling techniques, we have changed the name of this button to say configure, but it also includes the transformations and modeling choices. It'll be ordinary least squares unless you choose something else. So we usually just kind of bypass this and start our analysis with no transformation. Then we're going to go on to this fit summary screen, which really is something that sets Design Expert apart from other statistical packages, because this allows you to do, or it provides you with comparative statistics on a number of polynomial models, and it also provides you with a suggested model. You evaluate these, and then we are going to look at, go from there into the model screen and select the model that we want to do in-depth analysis on. And then we do analysis of variance. And I'll walk you through all of these things. And diagnostics, and then we draw some pictures, and then we do some final confirmation runs. So this is kind of all the steps that we'll be taking today, and I'll talk through all of these things. All right, so I'm going to switch quickly to actually Design Expert. I'll show you, this is the layout of our runs. You can see we've got the first 12 runs in block one. Actually, this was being split on over 2 machines. And we can, I'm going to just turn on an option called space point type that allows you to actually see which of the runs are the factorial points and which of the runs are the center points. And so you can see that the center points are our replicated points. Somebody asked, what does pure error mean? Pure error is the error that comes from exact replicates. So a center point replicated is going to give you an estimate of the pure error of the process, meaning nothing else is changing. The only thing that is going on is that you are replicating, you're repeating the same conditions over time. And so this really helps you figure out your natural process variation. So we would want to spread out these center points over time so you can get a good measure of the natural process variation. All right, then we go to the analysis, and we're going to click on analysis. And like I said, version 13 now calls this the configure screen, but it still gives you all of the transformation options. We're just going to leave this at no transformation and then continue to our fit summary screen. So our fit summary, we're going to look at these statistics. I'll flip back to the screen. We lay out p-values for each of the terms that are in these models. So we look at the linear terms in particular, and we do a test for their significance. And we find out that the linear terms are actually not statistically significant. The guideline is that the p-value should be less than 0.05, and you'll see that the linear terms on their own are not significant. So then we go on and we say, well, would adding two-factor interaction terms add information to the linear terms? And this is called a sequential p-value because we are actually testing the addition of the 2FI terms to the linear model. And you can see the addition of these terms is significant. So that's good information. We need some interactions. And then we test the significance of adding the quadratic terms to the 2FI model. And again, we see significance here. So this is good. Adding in cubic terms, there's no additional benefit for adding cubic terms. These are non-significant. So, so we don't have to go to a cubic model. Then there's another column called lack of fit. Lack of fit is basically telling you how much how well the model fits. And you want lack of fit, it's a double negative here, lack of fit to be not significant. So on this column, you prefer that the p-value be something greater than 0.1. You know, I don't really care how big it is, but greater than 0.1 is good. So you can see our quadratic model, which was looking significant, also has a very strong lack of fit. So this, or I'm sorry, a weak lack of fit. So it's not significant, and this is good. This indicates goodness of fit. I apologize for the double negatives there. That's a little hard to understand, but basically you want a higher p-value here. Then the last two columns, and I have another screen that will give a better definition of these R-squared values, but for right now, we want higher R-squareds, and you can see these are the higher numbers. And we also prefer that the difference between the actual and the predicted R-squared is less than 0.2, which it is. And so overall, this quadratic model becomes our suggested model. The software has an algorithm that it goes through and provides a suggested model. Notice that the cubic model says it's aliased. And I have a footnote here, do not select an aliased model because there are not enough runs to estimate all the coefficients for that model. We can estimate a few of them, and so we can get some statistics, but we don't have enough runs to estimate all of them. So never select a model that says it's aliased. You can't fit it all. It would not be appropriate. Okay, so the next thing we do, now that we know that suggested quadratic seems good, is we go to the model screen. And the model screen is where you can actually interact with the software, and you can choose which model. And it would default to the quadratic model because that is what is suggested. There is also, we'll come back here later, there's also an automatic model reduction tool, and we will return to this a little bit later on. So we're going to go from the model to the ANOVA screen, and we're going to look at the statistics and some of the information that is on this ANOVA screen. So I'm going to do that with the slides because it's just a little bit easier to see. Oh, I almost forgot. I did have, I put in a couple of extra slides on some extra information about that lack of fit test. Just kind of a sidebar here. Let's say that you had 6 design points. So I have a point 1, 2, 3, 4, 5, 6. And I do 2 runs at each of those design points. And I get the data as shown here, all the dots, that's the data. And I attempt to fit a linear model through that data. When I fit this linear model, I'm going to get a significant lack of fit. You can see that this model doesn't fit the data. If I then went ahead and fit a quadratic model, I'm going to have insignificant lack of fit. You can see how this model fits much, much better. The test is a test where we compare the variation between the actual data and the predicted value. So, we've got our actual data and we're comparing it to the prediction versus the variation between the replicates. So that says the MS of the pure error. This is the variation between the replicates. These 2 sources of variation should be similar in size, and then you'll get a non-significant lack of fit. Now, just as a hint, if you do not have any replicates in your response surface or mixture design, then you will not get this lack of fit test. Replicates are essential. You need a few. And by default, Design Expert is always going to give you replicates. Don't delete the replicates because you think they're not needed. Run them, randomize them throughout the whole experiment, and you will have a better analysis. You'll have more information and better analysis. All right. So here's that model screen that I was talking about, and then we will transition into the ANOVA. Okay, give me 1 second. Okay, we look at the ANOVA, and the key things here are to make sure that your p-value for the overall model, this is the overall model, shows it has 9 degrees of freedom. That means there's 9 things in here. That overall p-value is significant. Yay. We also look and make sure that the individual terms are significant. So I can see that I have many, many significant terms in here. So that is also good news. I have some insignificant terms also. I'm going to come back to that when I talk about model reduction, but for now, I'm just going to go forward with these. And then here's my official lack of fit test. And that is not significant, and that is also a good thing. Now, besides your basic analysis of variance, you also get some model summary statistics. They are in the upper right-hand corner of Design Expert. And one thing I like to check is the standard deviation. That is the amount of random variation left in the process after you've accounted for these model effects. So it's just the remaining variation, kind of a good baseline. The information that I'm really keying in on for response surface designs is the R-squareds. Here's a definition. The adjusted R-squared is the amount of variation in the data that is explained by the model. The amount of variation in the data that you collected that's explained by the model, and higher is better. Here we're saying we have about 88.8% of the variation in the data explained. So that leaves us with what, about 18% unexplained. Very, very good. The predicted R-squared is the amount of variation in predictions. You're going to use the model to make predictions. So how much of the variation in predictions is explained by the model? Again, higher is better. And the guideline rule of thumb is that these two should be within 0.2 of each other in order to show that the model is not overfit, that you don't have too many insignificant terms in your model. So our model fit is good. We're within 0.2. I could go ahead and use this model. From this, you then get some prediction equations, and I don't use the equations very often, but I know you guys like to put them in reports. I prefer to do my interpretation with the graphs. It's a lot easier to understand the graphs than the numbers. But in terms of using these equations, note that you have two of them. You have a prediction equation in terms of the coded factors. That would mean factors are set in that -1 to +1 range, the coded units. And then the equation in terms of actual factors means that you use the actual factor levels in this equation. Both of these equations are useful for making predictions, as long as you put in the right units. The coded equation is great for interpretation because you can see the relative effects of any of the terms. So I can see like my AC interaction actually contributes the most. That's a really, really strong interaction. And some of the smaller effects, main effects look smaller, but they're also crucially important because they're in these interactions. So in a response surface design, you have to take all of these terms into play when in order to understand the overall significance of things. The actual coefficients, you see that they are really strange. They are taking into account the factor ranges. So you can't interpret any of these coefficients. They are just not interpretable. There is a formula to convert back and forth, but you can't look at these numbers as raw numbers because they are both explaining the relationships and the factor ranges. So a factor that has a small range is going to naturally have a big coefficient, and a factor that has a big range is going to have a small coefficient. The equations to convert between these two are in the help system. Now, after you look at the ANOVA and confirm that you have good numbers, then it's super important to validate the ANOVA. And for model validation, we use diagnostic plots, residual diagnostic plots. So let me show you a screen first. The diagnostics are coming from we take the data, the observed values. This observed data has both important signal that we bring out of it by creating our model. We get our predictions. And it also has noise. There's also just random process variation in there. So we're really trying to strip that noise out by taking the difference between our observed values and our predictions. That difference is the noise, or we call it the residuals. Now, these residuals are the things that we verify are independent, normally distributed, with a mean of 0 and a constant variance. So those are those classic statistical assumptions that we want to verify with the diagnostic plots. So that's when we get to these diagnostics. And there are certain diagnostics that I use. I'm actually going to take this normal plot of residuals is great. Residuals versus predicted. Residuals versus run is kind of buried back here. It's behind this other one. I'm going to take that one and I'm actually going to pull it out. I can just drag and drop it right down here. So then I can look at it more easily. This normal plot of residuals allows you to verify normality. Your points should be on roughly a straight line. They do not have to be perfectly straight. You can see that's tailing off just a little bit here. As you see more and more of them, more of these graphs, you will see that this amount of variation is actually within normal bounds. There can be some up and down scatter. You don't want to see a big S-shaped curve, as that would indicate non-normality. Over on the residuals versus predicted graph, you can check for constant variance, which means that the up and down spread of the residuals from the small predictions is about the same as the up and down scatter when you make large predictions. And so it's just a random scatter here. There's no big expanding trend. And so a random scatter is going to verify that you have constant variance across the design space or across the predictions. Going down to the residuals versus run, again, just randomization, no patterns. In addition, on both of these graphs, we have the ability to check for outliers. And so there are no outliers, nothing, no points outside those red lines. And finally, a favorite graph. If you don't look at any other graph, look at this. The Box-Cox plot tells you if you need a data transformation. Remember that very first screen we were looking at? This says recommended transform, none. So you do not need a data transform. If it said log, you would go back and apply a log transform. If it said inverse, you would go back to this beginning screen and put on an inverse transform. So whatever it says, that is what you should do. And it's very important that you do watch that, look for transformations. We have other webinars that go through these diagnostics more in depth, so you can look for them on our website. And in the slides, there'll be a summary of this. We're looking for a fairly straight line. We're looking for no particular patterns on any of the rest of these and no transformation needed. Now, in the lower right-hand corner, Design Expert, we also have influence graphs. And I've pulled out those influence graphs. The Cook's distance, the leverage, the DF fits, and the DF betas. First of all, influence. means that it measures simply the influence of each point. People jump to thinking that influence is bad. If you have influence on another person, that's not a bad thing. That's just that you have some pressure or some say in what they're doing. But if the other diagnostic plots are showing all good results, then you don't have to look at the influence graphs. Okay? If there are no outliers, you do not need to look at the influence plots. But just to cover these, you have the Cook's distance, which is giving you the change in the model fit with and without a particular point. The DF fits gives you the change in predictions. So that's the fitted model, change in predictions with and without a particular point. DF betas is the change in each coefficient with and without a point. So actually, look, this is a DF betas for factor A. There's a little pull down arrow here that you can change. You would change it to coefficient A, B, C, etc., all the way through. So this is actually about 10 different graphs in here. And then leverage is actually the change in predictions due to a point's position in the design space. So leverage is a little bit special case. It's a design measure, whereas all the rest of them are data measures. The other graph, the last one, is a predicted versus actual plot, which is purely taking your predicted values versus your actual values, plotting them against each other. And if you are fitting really, really well, the 45-degree line will fit right along those points, or the points will fit right along that line. So this is a good indication of how well your R-squared is. The higher your R-squared, the more tightly these points are going to fit along that line. All right. Now, at this point, rather than looking at model graphs, I'm going to back up and I'm going to go back and cover model reduction for just a couple of minutes, because we did see that we had a couple of non-significant terms in the model. And I recommend that we always remove insignificant terms. It honestly does not matter if you have just a small percentage of terms not significant, but if you have a lot of insignificant terms, then it can make a big difference in the prediction results. So Design Expert offers four statistical criteria, and several selection methods for doing automatic model reduction. Now, we have p-values. This is a real classic method. I'm going to demonstrate this to you in just a second. But p-values, usually you want smaller p-values in general. There is a couple of new statistics called AICC and BIC. These are goodness of fit statistics, and the actual statistical criterion is kind of difficult, so I'll leave that to you to Google that and check out what those equations are. But AICC is a small sample correction to this particular statistic. All of these methods are going to work well if you have a design that has little correlation, or collinearity we call it. If your design has more correlation, then we're going to recommend actually doing a few of these, try them, and compare the different models and see if the results differ. The selection methods are backward and forward and then stepwise. Again, bear with me, I will demonstrate these. The backward method starts with all model terms, like it would start with the full quadratic model. It would eliminate the term that is worst from a statistical point of view, whether that's using p-value criteria or the AICC criteria. And then it's going to recalculate. And then it's going to eliminate the next worst term and recalculate. And it continues eliminating terms until the stopping condition is met. Forward is going to start with the term that's most correlated with response, and then it's going to add another term. It will calculate the statistical criterion. It will add another term and recalculate, and it'll keep adding terms that add value to the model until your stopping condition is met. And then stepwise starts forward, recalculates, it goes backward if needed, then it goes forward again, and it goes backward. So it's really a double loop going forward and backward until your stopping condition is met. All right, so let me demonstrate this. I'm going back to the model screen. We've got the full quadratic model selected. I'm going to click on auto select, and I've got the AICC backward method chosen. If I click start, then it says it's going to select AB to be excluded, and then it's going to select A squared to be excluded, etc. So it tells you what it's doing, and at the end you just click accept, and it removes terms. Now what it does not do is it does not test for hierarchy during that model reduction method. But maintaining model hierarchy is really, really important. So I can see at a glance that I have an AB interaction. I also have A squared, but that model reduction method took out the A term. I want A to be in the model. So when I click on the ANOVA screen, it's going to say the model you've selected is not hierarchical. Would you like hierarchy corrected automatically? The correct answer is yes. You just always say yes. And it adds A back into the model. So now I can see that this model does not have that AB term. It does not have the A squared term. It does have A in it. So we're keeping A for hierarchy. That is needed for these other to help out with these other significant terms. We double check that lack of fit is still not significant, and we double check our adjusted and predicted R squareds. And normally what's going to happen is that the difference between these two is going to tighten up. It's going to become even smaller than it was before. You would also then go through and double check your diagnostics to make sure that they are all still good. So we are in good shape. You could also try a different selection method. Whenever you try a different method, you need to reset the process order to quadratic or to whatever your original one is, and then go to auto select, and maybe I would check p-value backward and start that. It tells me what it did. I just say accept, and I click on ANOVA. I say yes to hierarchy, and then I'm going to get the exact same answer. Like I said before, if you have a nice design with little correlation, then you're going to get the same results no matter which criteria you use. So you ultimately end up using those prediction models to create your graphs. And you can have contour graphs. You can have, I'm going to add a 3D surface graph in here. So now I've got both contour and 3D surface. I did that by clicking the little plus, add new graph, so I can add additional graphs onto here. And you look at these in whatever dimensions that you want to, and you find the best settings. So here I put them side by side. I'm trying to maximize my percent conversion. And so the maximum value is over on this side in the BC direction. And over here, a little bit, you can see that hump. And so, you know, these would be the best settings. Now, many of you guys stop at this point. You know, you find your best settings and say, okay, this is where, you know, I end. There is a critical next stage. Your final step should actually be confirmation runs. And Design Expert provides a place for you to put the confirmation runs. So the final stage is to confirm that the model predictions are accurate in your original process. You can do a few runs either at your optimum condition or across the whole design space, you know, whatever your interest is. And some people are looking for a very particular spot to run. Some people are looking to confirm that the model predicts well across the entire design space. So confirm the area that's of interest to you. Enter the data into the confirmation node and verify that the mean of those runs falls within the 95% prediction interval. So I'll show you this live here in a second, but what we're going to do is click on confirmation. It allows you to enter your process conditions. So you type in the location that you want. Then you type in your response data. So in this case, I did 4 runs, so I put in that information. And then it is going to tell me the average, the predicted mean for those 4 runs. And it gives me the prediction interval, a 95% interval, and you want that mean to be within, sorry, this is the data mean, to be within that interval. So this is the mean of those 4 runs. This is actually the predicted mean for that location. So that is down here under post analysis, confirmation. I've got my confirmation location here. I've got my 4 runs in here. And I've got the prediction for that particular spot should be 96.8. When I did 4 runs at that spot, I actually got 92.6. That is between the 87 and 105, so I am good to go. You know, your average is very rarely going to be exactly what you predict, but that's why we give you a prediction interval. Now, if you needed to do multiple locations, there's this little arrow here. You can pull that down and choose add location. And I could do location number 2. You know, maybe I would change my time to 55. Oh, that was outside my design space. Be 65. I do not have a clear definition of what my design space is. I'll change temperature to 85. There, that's within my design space. And again, then I could put in response data for that location, and I would get another another set. And so you could add, as many locations as you want to. Okay. So one question is, what if confirmation fails? Consider the following. Was your analysis good? Did you have good p-values? Did you have some lack of fit issues? Did you have a good predicted R-squared? Were the diagnostics good? Did you do model reduction? So back to the analysis. Was it a good analysis? Then consider the process. Did the process shift? Was it stable? Then are there any other process factors that might affect your system, that you didn't include in this experiment? Basically, if the confirmation fails, you need to take an engineering or science look at the system and decide how you can get better data. You might be able to add additional data into this existing data set in order to improve it, or you might have to do just an entirely new experiment. Okay, so before I wrap this up, let me just open up the question pane and see if I can answer some of these questions. I might not get to everybody's. Somebody asked how to interpret the contour plot. So let me just switch back to the contour plot. The contour plot has factors on each of the X and Y axes. So I have time and catalyst, and it shows the response line as it's like a topographical map. So I have 80, 90, etc. I'm going to close this one. So it's a little bit bigger. And you could even add contours into this. And in this case, I was trying to maximize my conversion. So I'm looking to go towards the red zone, the red area. Higher is better. So, I mean, you just have to read the axes, read what's on the graph, and you guys will figure that out. Somebody else asked about that question about the confirmation. And let me go back to just location 1 and said, my 92 is not the same as 96. It does not need to be. The fact that the 92 is within this interval means that you confirmed. You confirmed that the prediction equation is predicting correctly. You have to remember statistics is all about ranges, intervals. It's not about a particular point. And I am not going to go back to the process and do this exact point and get 96.8. I'm going to get some variation around that point. And this is the range, 87 to 105. Now, if you don't like how big that range is, then that's inherent in the process. You have to improve the process to improve that range. So you need to really just focus on the data mean, and focus on the prediction interval, the interval itself, and don't focus on that mean. The prediction mean is your expected mean, but the prediction interval is the range around that in which a mean could fall. It's an interval. It's not a specific point. There is also the numerical optimization tool. We have other webinars on that will show how to use that numerical optimization, so I'm not going to take the time to cover that here. Somebody noticed that when we reduced the model, the R squared decreased. I don't remember exactly. It probably did not change by very much. It might have changed by a little, but remember, you know, we are improving the accuracy. Usually, what will happen is that your predicted R squared, which is your ability to make predictions, will increase. It should increase as you do model reduction, and that's really the most important thing. Okay, if I didn't get to your question, then I will try to follow up with an email. Just to summarize, you know, again, you start with your transformation, which is normally none. You start with none. Then you look at the fit summary and especially evaluate that suggested model. It should be the best one. Then you go to the model screen and allow that suggested model to be chosen. Check the p-values and the lack of fit and the R-squareds and the ANOVA. Validate your ANOVA using diagnostics. View the model graphs and find your optimum conditions. You might use numerical optimization also to find your optimum conditions. And then go back to the process and do confirmation runs. And you saw I did four runs. So don't just do one run, do 4 to 6. You know, there's no specific recommendation, except I'll say more than one. And you know, somewhere 4 to 8 runs is probably about enough runs to do. All statistical analysis should be guided by subject matter knowledge. Does it make sense that the given terms are significant? Do your model graphs reflect the actual process? Do the confirmation runs verify the analysis? You know, subject matter knowledge is key, and that's why we encourage you to go back and do the confirmation runs at the end. All right, so Design Expert 13 is now available as a free trial. If you are a student, a university student, you can apply for a low-cost academic license. Our trials are not intended to be used to complete work. They're not long enough to do that, so please apply for an academic license to do that. And next week, Martin is going to unveil the tools that are specifically new in Design Expert version 13, so you can come back next week. And then in March, we'll be doing a webinar on the Poisson regression tool for analyzing count data. And count data would be something like counting up manufacturing defects or any sort of response where you're actually counting the number of occurrences of the response. If you really want to benefit from training, you'll come to one of our more in-depth classes. We are happy to host these classes specifically for a company. Works well if you have at least 6 people there. We can really customize the classes to meet your needs, even adding company case studies if you want. So you can learn more about all of our public and private classes on our website, staties.com, or email us if you have any specific questions. The more information about response surface analysis can be found in our RSM Simplified textbook. That is available from the publisher, Taylor and Francis. There's a link to it from our website. Also, you can find it on Amazon, and it's available for those of you who are coming in internationally. You can rent an ebook for just a short period of time, and that is a pretty low cost option. So I would like to thank all of you for listening today. If I didn't get to your question, I will be sure to send you an email as a follow-up. You can email me, or you can email stathelp@statease.com, and I'll be happy to answer additional questions that you have. So with that, I would again just like to thank you for attending, and wish you the very best in your day.